Yeah, good evening to all. It is Navneet Krishnan from iitiansgateclasses. In this section, we'll be dealing with flight performance gate problems of 2018. Okay. 2018, question number 4. A jet aircraft initially flying at a steady level flight at its maximum endurance condition. For the aircraft to fly steady and level, but to fly faster at the same altitude, pilot should option A increase thrust alone, option B increase thrust and increase angle of attack, option C increase thrust and reduce angle of attack, option D reduce angle of attack alone. Okay. What is the endurance condition for jet engine aircraft according to Biscuit range endurance equation? The endurance of jet engine aircraft is given as endurance equal to 1 by thrust specific fuel consumption into CL by CD into ln of W0 by W1. They told maximum endurance condition, that means Emax. Emax corresponds to CL by CD max, which is drag minimum condition, which is nothing but CD not equal to CDI. Okay. This is what maximum endurance condition is. They told that they are flying in a steady level flight, that is lift equal to weight, thrust equal to drag. But now we have to fly at a faster speed at the same altitude. That means what? Lift increases. Not only lift increases, drag also increases. Because lift and drag both are directly proportional to V square. When velocity increases, both lift and drag increases. Now, we have to fly at the same altitude, but also fly at a steady and level flight, but fly faster. Which means that if lift increases, then lift is nothing but CL into half rho V square S. To maintain steady level flight, that is lift equal to weight, velocity it has increased. That means only way to maintain steady level flight is it has to decrease CL. So how we can decrease CL? By reducing the angle of attack. By reducing alpha, CL can be decreased. Thereby we can maintain steady level flight. Next, if you take this component, drag increased. To maintain the steady level flight, thrust equal to drag. What happens? Then we have to increase the thrust. So in order to overcome the drag, we have to increase the thrust. In order to maintain the same altitude, we have to reduce the lift by reducing the angle of attack, by reducing the CL. That means option C is the correct answer. Any doubt? Any doubt in this problem? Next. So option C is the correct answer. GATE 2018, question number 5. The pilot of a conventional airplane that is flying steady and level at some altitude deflects port side aileron up, starboard side aileron down. The aircraft will then, option A, pitch up, pitch up, that is nose up. Option B, roll with the starboard wing up. Option C, pitch nose down. Option D, roll with port wing up. First of all, in order to pitch up or pitch down, only elevator deflection is required. So with the help of elevator deflection only, we can nose up or nose down. So option A and C are form. Now we'll see. If you take an aircraft, the right side wing is called as starboard wing. The left side wing is called as port wing. Okay. Here they have mentioned port side aileron, they have deflected up. Port side aileron, they have deflected up. Starboard side aileron, they deflected down. That means port side aileron, it is deflected up. That means it is having negative camber. That means lift decreased. Okay. Lift is decreased. Already there is some lift due to the camber of the wing. But when you are deflecting aileron, the lift is getting reduced because the camber is getting reduced. Thereby, lift on this wing is reduced. Okay. If you see the starboard wing, it is deflected downward. So what happens? The line joining leading edge and trailing edge is called as chord line. The midpoint between upper surface and lower surface is called as camber line. This is your camber line. This is your chord line. So camber got increased. So camber got increased means the lift on that wing will increase. So the differential will lift. What happens? The differential lift on this wing is got increased. The lift on this wing is reduced. So the differential lift will cause a rolling moment towards port side. That means starboard wing is going up. So it's a roll with starboard wing going up. Yes, Satish, correct answer. Option B is the correct answer. Any doubt? Gate 2018, question number 6. The NACA 0012 aerofoil has a trailing edge flap. The aerofoil is operating at an angle of attack of 5 degrees with undeflected flap. If the flap is now deflected 5 degrees downwards, the CL versus alpha curve, option A, shifts right and slope increases. Option B, shifts left and slope increases. Option C, shifts left and slope stays the same. Option D, shifts right and slope stays the same. Okay. First, NACA 0012 aerofoil is a symmetrical aerofoil because first 2 digits represents camber of the aerofoil. Where it is located, how much is the camber. So since first 2 digits are 0, it is a symmetrical aerofoil. For a symmetrical aerofoil, the CL versus alpha, if you take, lift at 0 angle of attack is 0. Then as angle of attack increases, lift increases. This is your alpha stall angle. Okay. Now, when you deflect the aileron at 5 degree, see, if you see here, at 5 degree angle of attack, this was your lift coefficient. Now, the aileron is, that is the flap is deflected downward. There is a flap which is deflected downward. When it is deflected downward, the camber gets increased. That means even at 0 angle of attack, it will produce lift. That means it will have 0 lift at the negative angle of attack. That means the curve shifts leftward like this, but the slope remains same because we have not changed the aerofoil. Only when the aerofoil changes, the lift curve slope changes. Since the aerofoil is not changed, the lift curve slope is not changed. So this is the new stalling angle of attack. The lift curve slope remains same. So lift curve slope AW of the wing remains same. Lift curve slope remains same, but the curve shifts towards the left, and it lift at zero angle of attack is zero. That is CL at zero angle of attack is zero when it is undeflected portion. When the flap is undeflected portion, when the flap is deflected downward by 5 degrees, what happens? The lift at zero, there is a positive lift at zero angle of attack. There is a positive lift at zero angle of attack. The curve shifts leftward and the lift curve slope remains same. So option C is the correct answer. Is that clear? Any doubt? Okay. Next. Question number 7. An airplane requires longer ground roll to lift off on hot summer days because the thrust is directly proportional to free stream density. The thrust is directly proportional to weight of the aircraft. C. The lift-off distance is directly proportional to free stream density. The runway friction between is high on hot summer days. If you say lift-off distance, the lift-off distance can be expressed as according to Anderson, the lift-off distance can be expressed as following. S lift-off is equal to 1.44 W square by G into rho infinity S CL max into thrust minus drag plus mu r into W minus L. This average force is calculated at 0.7 V liftoff. So V liftoff is equal to 1.2 times of V stall. At 1.2 times of V stalling velocity into multiplied by 0.7, these forces are calculated. All these forces are calculated. Now, if I assume, since thrust is far greater than this component, we can assume that S liftoff distance is directly proportional to G into 1.44 W square by G into rho infinity S CL max into thrust. So we can neglect this component as in this way. We know that thrust is directly proportional to density of the aircraft. Sorry, density of the air. Thrust is directly proportional to density of the air, because thrust is directly proportional to mass flow rate of air entering the engine. So thrust is directly proportional to density. Already there is a term called as density here. So S liftoff is inversely proportional to density square, because thrust is a function of density. So there is one density term. So density into density, density square. If you see hot summer days, during hot summer days, the air density becomes less. Due to humidity, on hot summer days, density is less. When density is less, what happens? The lift-off distance increases. Okay. So during hot summer days, the lift-off distance increases. So if you see, only way it is doing this, the lift-off distance is inversely proportional to density. So this option C is wrong, because it is not directly proportional to density. It is inversely proportional to density. It doesn't depend upon the, even if the friction is high, that means it is reducing this component, that is lift-off distance is increased. So here the frictional coefficient is not that much plays a role on the thrust of an that is lift-off distance of an aircraft. So option D is also wrong. Thrust is not directly proportional to weight. This option is also wrong. Thrust is directly proportional to free stream density because thrust is directly proportional to mass flow rate of air entering the engine. So that means mass is directly proportional to density. So thrust is directly proportional to free stream density. Option A is the correct answer. Okay. Any doubt? Next question. Question number 12. The pitching moment of a positive cambered NACA airfoil, okay, about its leading edge at zero lift angle of attack is about its leading edge of at a zero lift angle of attack is option A negative, option B positive, option C indeterminate, option D 0. Yes, Tangamuthu, it is option A is the correct answer. Why means all the NACA airfoils, if you take, it's a positive cambered airfoil. Generally, wing, we use a positive cambered airfoil. Okay, positive cambered airfoil. If you take positive cambered airfoil, the lift will be always acting at the aerodynamic center location. For NACA airfoils or any subsonic airfoils, if you take, the aerodynamic center lies at the quarter chord point. For supersonic flow, it lies at the half chord point. That is 1/2 of C. Now, the lift and drag is acting at this point. Lift and drag is acting at this point. If you take a moment about leading edge of the wing, that means it is providing your nose down moment. It is providing your nose down moment towards leading edge of the wing. No, nose up moment is positive. According to sign convention, nose up moment is positive. Nose down moment is negative. So option A is the correct answer. Because it is having a nose down moment, that means it's a negative moment. So option A is the correct answer. Any doubt? Okay. Question number 16. The highest limit load factor experienced by the civilian aircraft is in the range of dash. The highest. Okay. For this to answer, if you see flight envelope, N1 is the highest load factor the aircraft is experienced. N1 is the highest load factor the aircraft can experience. So, if you see the flight envelope, load factor versus velocity. This is how your flight envelope looks like. So, this is N1. This is N2. This is N3. Now, if you see the highest load factor experienced by the airplane is N1. Now, they are given for different category of aircraft. What is N1, N2, N3? So, N1, N2, N3 for different category of aircraft. If I take a normal category aircraft, normal civilian transport aircraft or normal civilian passenger aircraft, the maximum load factor it can experience is 2.1 plus 24,000 divided by weight by 10,000. Sorry, weight plus 10,000. Weight plus 10,000. If you take semi-acrobatic aircraft, the maximum load factor experience is 4.5. If you take acrobatic aircraft, that is fully like for air shows and all you usually use, right? That is called as acrobatic aircraft. 6 is the maximum load factor. N2 for normal aircraft is 0.75 times of N1, but it is always less than or equal to 2.0. For semi-acrobatic aircraft, it is 3.1. For acrobatic aircraft, it is 4.5. N3 is the negative load factor the aircraft will experience. For normal aircraft, it is minus 1.0. For semi-acrobatic aircraft, it is minus 1.8. For acrobatic aircraft, it is minus 3.0. So if you see the normal category aircraft, that is your civilian aircraft, that is either it can be passenger or transport aircraft. The load factor it experiences always greater than the maximum load factor it experiences always greater than 2. That means it lies in the range of 2 to 5. So option B is the correct answer. Okay. It lies in the range of 2 to 5, which is option B is the correct answer. If you take fully acrobatic aircraft, it lies in the range of 5 to 8. Okay. Next. Question number 33. An aircraft with a turboprop engine produces a thrust of 500 Newton and flies at 100 meter per second. If the propeller efficiency is 0.5, the shaft power produced by the engine is option A 50 kilowatts, option B 100 kilowatts, option C 125 kilowatts, option D 500 kilowatts. Now, if you see for turboprop aircraft, power available is given by eta P into the efficiency of the propeller into shaft power. So they asked us to find out what is shaft power. Shaft power is nothing but power available efficiency of the propeller. Power available is nothing but thrust into velocity divided by efficiency of the propeller. What is the thrust? 500 Newton. What is the velocity? 100 meter per second. What is the efficiency of the propeller? 0.5. It is given. So what happens? It will become 1 lakh watts. 1 lakh watts. It is nothing but 100 kilowatts. It is nothing but 100 kilowatts. So option B is the correct answer. Yes, option B is the correct. Any doubt? Question number 38. Question number 38. Assuming ISA standard sea level condition, where temperature is 288.16 Kelvin, density equal to 1.225 kilogram per meter cube, acceleration due to gravity is 9.81 meter per second square, or gas constant equal to 287 joule per kilogram Kelvin. Density of air in lay, which is at an altitude of 3,500 meter above mean sea level is dash. Accurate to 2 decimal places. So, if you have to find out what is the temperature, what is the density at 3,500 meter at lay is, it is troposphere. That is 3,500 meter lies in the troposphere. So we can use troposphere relation. What is the troposphere relation? Rho by rho infinity equal to T by T infinity power T by lambda r minus 1. So first we have to find out what is T at that altitude, temperature at that altitude. Temperature at that altitude is T infinity minus lambda x, where T infinity is the temperature at sea level, 288.16 Kelvin, minus lapse rate at that troposphere is 0.0065. Altitude is 3,500 meters. Substituting that, I get temperature as 265.41 Kelvin. Substitute everything in this. We have to find out what is the density. But density at sea level is 1.225. Temperature just now we have found out 265.41. Temperature at sea level is 288.16 power. Acceleration due to gravity is 9.81 divided by lambda is 0.0065 into 287 is the gas constant minus 1. Substituting this, we get density as, yes, correct, the number 0.863 kilogram per meter cube. If I round off to 2 decimal places, it is approximately 0.86 kilogram per meter cube. So, answer is 0.86. Okay. Any doubt? Next. Question number 40. An aircraft with a mass of 4 lakh kg cruises at 240 meters per second at an altitude of 10 kilometers. Its lift to drag ratio is 15. Assuming acceleration due to gravity is 9.81 meters per second square, the power in megawatts needed for it to cruise is dash, accurate to 2 decimal places. During cruise, we travel in a steady level flight. That is lift equal to weight, thrust equal to drag. So, lift by weight equal to 1, drag by thrust equal to 1. If I equate, I can write it as lift by weight equal to drag by thrust. Yes, correct, Satish. So thrust is nothing but, if I take thrust on the other side, it is nothing but drag by lift into weight. So I can rewrite it as weight divided by L by D. That is your thrust. Now we have to calculate what is the power. Power is nothing but thrust into velocity. Thrust we just now calculated, it is W by L by D into velocity. W should be in Newton. So W here it is given in the form of mass 4 lakh kg. That means to convert into Newton, we have to multiply it by 9.81. So weight is nothing but 4 lakh into 9.81 is the weight. Into velocity is nothing but 240 meters per second. Divided by L by D is 15. So we get power as 62784,000 watts. If I have to get in megawatts, then it is 10 power 6 watts. So it is 62.784 into 10 power 6 watts. 62.784 into 10 power 6 watts. That means 62.784 megawatts. Okay. If I round up to two decimal places, it is 62.78 megawatts. Yes, 62.78 megawatts. Okay. Next. Question number 42. An aircraft with a gross weight of 2000 kg has a speed of 130 meter per second at sea level, where the conditions are 1 atmospheric pressure, temperature is 288 Kelvin, and density equal to 1.23 kilogram per meter cube. The speed required by the aircraft at the altitude of 9000 meters. They asked us to find out what is the speed at 9000 meters, where the conditions are 0.31 atmosphere, temperature equal to 230 Kelvin, and density equal to 0.47 kilogram per meter cube. To maintain a steady level flight is dash. Accurate to two decimal places. First of all, what is 1 atmospheric pressure is? 1 atmosphere is equal to 101,325 Pascal. That is 101,325 Newton per meter square is the meaning of 1 atmosphere. Okay. Now we have to calculate what is the speed at that altitude. In order to find what is the speed at that altitude, it is nothing but 2W by rho s CL. We know what is the density at that altitude. It is directly given. It is 0.47 kilogram per meter cube. We know weight. It is 2000 kg. If I convert into Newton, it is 2000 into 9.81. But we doesn't know what is the area and CL. In order to find out, they have already given what is the speed at the sea level. Speed at the sea level is given as 2W by rho infinity SCL. If I square this term, V infinity square, it is 2W by rho infinity SCL. Yes, correct, Tanyamutu. 210 meter per second. So velocity they given as 130 meter per second. So 130 square into 2 into weight. Weight is nothing but mass into acceleration due to gravity. Mass is 2000 kg into acceleration due to gravity is 9.81 divided by rho infinity. They are given it as 1.23 kilogram per meter cube. 1.23 kilogram per meter cube into S into CL is an unknown value. So we only unknown is S into CL. So we can find S into CL at 1.8877 is the value of S into CL. Substitute in this equation the value of S into CL, we get velocity at that altitude. So velocity at that altitude is root of 2 into weight. Weight is 2000 into 9.81 divided by rho they given it as at that altitude is 0.47 kilogram per meter. Into S into CL is 1.8877. So we get velocity at that altitude as 210.305 meter per second. If I round off to two decimal places, I can write it as 210.31 meter per second. Okay. It is 210.31 0.31 meter per second. Any doubt? Yes, Ashish, you have some doubt? Yeah, you can use the relative density directly also. No issue. That is rho by rho infinity into. Okay. You can use that. No issue. Question number 43. A pitot prop on an aircraft in a steady level flight may records a pressure of 55,000 Newton per meter square. The static pressure and density are 45,280 Newton per meter square and 0.6 kilogram per meter cube. The wing area and the lift coefficient are 16 meters square and 2 respectively. The wing loading on this aircraft is dash. Okay. They asked us to find out what is W by S. That is called as wing loading. For a steady level flight, W can be written as lift. Lift divided by S. That's what we are learning. Lift can be written as CL into half rho V square S divided by S. So CL into half rho V square. Yes, correct. 19440 Newton per meter square. So CL is, we know that it is given as 2. CL is given as 2. 2 into 1 by 2. Density, they are given it as 0.6 kilogram per meter. 0.6. We have to find out what is the velocity in order to find out what is the wing loading. To find out what is the velocity, they told that Pitot prop. Pitot prop means Pitot tube. Pitot tube generally measures static pressure or stagnation pressure. Pitot static tube measures dynamic pressure. So Pitot tube generally measures total pressure. Pitot static tube measures the differential pressure, stagnation minus static pressure. So they have mentioned Pitot prop. So Pitot prop velocity for an aircraft can be written as 2 into P naught minus P by rho. So 2 into P naught is 55,000 because Pitot prop measures pressure of 55,000. The static pressure it can measure is at the altitude 45,280 divided by density is 0.6. So we get the velocity as 180 meter per second. Substitute it here. So 2 divided by 2 can be cancelled. So it is 0.6 into 180 square, which is nothing but 19,440 Newton per meter square. Yes. Any doubt? Satish, do you have some doubt?
So the dynamic pressure we can directly get it from P naught minus P.
Yeah, but we are not having dynamic pressure directly because only Pitot prop is
No. What I'm saying in that equation, 2 into half rho V square is there. No. For half rho V square, it is nothing but P naught minus P.
Yes, we can put it directly.
Minus 45
we can put it directly that way.
Yeah.
No issue. Yeah, P naught minus P is nothing but half rho V square. So we can put directly here for half rho V square as P naught minus P. That way also we can solve. Next, question number 48. The gross weight of an airplane is 7,000 Newton. Wing area is 16 meter square, and the maximum lift coefficient is 2.0. Assuming air density at that altitude as 1.23 kilogram per meter cube, the stall speed in meter per second of the aircraft is dash, accurate to 2 decimal places. What is the stalling speed of an aircraft? It is nothing but root of 2W by rho S CL max. Yes, Abdullah, you have some doubt? So, weight is we known as 7,000 Newton. Yes, Sadish and Tanutu, it is correct answer. Density is given as 1.23. Wing area is 16. CL max equal to 2. Substituting that, we get Vstall as 18.86 meter per second. So it is 18.86 meter per second. Any doubt? If you have any doubt, you can ask. Otherwise, we are winding up this section. So we have solved GATE 2018 performance problems. If you have any doubt, you can ask. Otherwise, we'll wind up this. Thank you. Yes, Ashish. You have some doubt? Ashish. If they have asked us to round off to 2 decimal places, you round off to 2 decimal places. But generally, it is if they are not given anything, round up to 3 decimal places. If they are not given anything, please round up to 3 decimal places. My screen is not visible. Okay. Sir, how decreasing aspect ratio of the wing will increase longitudinal stability? Who told that decreasing aspect ratio of wing will increase longitudinal stability? See, Akash, longitudinal stability for wing alone is Cm alpha is AW into H minus HAC. For aircraft is minus AW into HM minus H. So it depends upon the neutral point of the aircraft, okay, and CG location of the aircraft. So Cm alpha is negative only for an aircraft to be longitudinally stable. Yeah, lift curve slope, yeah, correct. Lift curve slope depends upon aspect ratio. Lift curve slope depends upon aspect ratio. As aspect ratio increases, what happens? When aspect ratio increases, this is the aspect ratio. When aspect ratio is equal to infinity, this. When aspect ratio is equal to 10, or aspect ratio equal to 2. Here, the lift curve slope is less. Here, the lift curve slope is more. Okay. Okay. Now, if you see, the lift curve slope has decreased when aspect ratio decreased. That means when aspect ratio is decreased, the lift coast load decreases, thereby Cm alpha decreases, thereby your stability decreases. Okay. This is CL versus CL versus alpha. Okay. Any doubt? Okay. So we'll wind up today's class. Thank you.